Did you know that you're made of a lot of water? I know you do. You know that. Babies are squishy and puffy and bouncy and jiggly because they have a lot more water than grown-ups. In fact, babies are about 70% or more water. Notice how I said that. I'm not trying to be picky with this number. I'm just telling you that most babies, their water content is in the 70 percentiles. And what happens is as we age, we lose water. We dry up. You know, old people, they're all wrinkly because they ain't got enough water in them. They're all dried up. If you're an adult male, you're probably in the 60s for your water percentage. And if you're an adult female, you're probably in the 50s. Okay? Men typically carry more water content because for their body size, they usually have more muscle, lean body mass, and that holds more water. Doesn't mean the muscles have to be huge to hold water. It's just body composition. Okay? Funny thing. As we age, whether you're male or female, I don't know if you've ever seen this, you know, really old folks, whether they're male or female, sometimes their profile or their silhouette kind of looks the same, you know, and that could be for any person, but it's more common with older people because as your hormone levels drop, those hormones are responsible for some of the ways that we look different as gender commonly. So as hormone levels drop, it changes body comp and it also changes water composition. So just notice that. If people make it to be real old, their water typically drops below 50. So my recommendation, even though I didn't draw on this, take a picture so you have it in your notes. You see a lot of numbers. I'm not going to try to pound you with numbers on this, okay? What I am going to do is I'm going to talk about important things that you already know. Like, what's that supposed to be? Capillary. And, oh, let me change that. Let's do a bigger one. And what's the name of the fluid component inside the blood vessel? Yeah. Plasma, right? So we know that's a capillary. We know there's blood in there, but we know, we might remember from way back, that plasma is about 55% of your blood. And if you have 5 liters of blood, that means around 3 liters of plasma, okay? So that's the number we're going to give you for plasma. Is about 3 liters. Now, remember, I'm not going to pound you with all these numbers, but there are some numbers that I do want you to think about and understand, okay? I'm going to have a second slide that's a visual of this. So the same content we're doing here is going to be on the next slide too, because I really want to lock in the few things that I'm going to do here. What this topic is it's where is your water in your body? And basically water is in 2 locations. What is that supposed to be? Come on, you can do it. Think day one. Day one of A&P. Somebody draws a circle on the board. What is it? A cell. Good. Yeah, it's a cell. So you have water in your cells, okay? And we call the area in your cells a compartment. And we call that fluid in there some kind of fluid. So both the compartment and the fluid have the same name. It's called intracellular. You guys remember what intra means? Inside. So intracellular means inside. So here's what I want you to know about the intracellular fluid, ICF. It is about 2/3 of your water. I'm not going to make you memorize the number, just 2/3. Okay, that's about what percentage? What's 2/3? A little less than 70, 60, 66.667, whatever, 67%, somewhere around there, a little less than 70. 2/3 of your water is inside your cells. How much is outside? If 2/3 is inside, how much is outside? 1/3. Yeah, cool. And the outer fluid, that E stands for extra. Extra means outside. Intra, inside, extra, outside. So your extracellular fluid, 1/3 of your body water is outside of your cells. So if you're 50% water, 2/3 of that water is found in your cells, and 1/3 of that water is found outside your cells. When you think of your body and where water is, most of us think of the blood right away. Because in AMP2, we've been doing blood so much. We talk about blood, we talk about the importance of blood, we're always talking about blood, so we think about blood. But look, this number you don't need. I'm just showing it to you right now. I'm not even going to highlight, I'm just showing it to you so you get an idea. Man, that's not much water in your blood compared to how much water you have in the whole body. Would that be inside your cells or outside of your cells? Outside, right? It has to be outside. Why? Because we have cells in the blood. So the blood's outside of those cells, right? So plasma is one of your major extracellular fluids. Okay? The other, and you did lymphatics on your own, so I don't know how up on lymphatics you are, but I'm going to draw this little green vessel like that and just say lymph, just to remind you, we have lymphatics out there, and I'm going to draw some other little circles. Hey, what are these circles out in the body? Cells, right? So we're talking about fluid outside the cells. Do you know what you call the fluid where I'm putting these little black dots? So that extracellular, it's okay, but it's not particular enough, because extracellular also would include the fluid in your eyes and the fluid in all your little joints and any other little weird area in your body. And extracellular includes plasma. What could we call the fluid outside of your cells that would only be that little space outside of a cell? Oh, interstitial fluid. Maybe you remember that. So out here, now I'm going to do this. If I can find the eraser, I'll just put ISF. And I'm going to come over here and put fluid outside of the cells is actually classified as interstitial fluid. And I'm going to tell you this. Hopefully it'll help you with the number. Interstitial fluid is 4 times more than plasma. So if you have 3 liters of plasma, how much interstitial fluid do you have? 12. Okay? So that's the relationship I want you to have, that you have 4 times more interstitial fluid than you have plasma. So you may be asked about the 3 liters of plasma on the test. You may be asked about the relationship between interstitial fluid and plasma on the test. Here's why. Those are your 2 major extracellular fluids, interstitial fluid and plasma. Good news for you, inside the cell, intracellular, it's only one place. It doesn't have a bunch of compartments. It's just inside of every cell is about 2/3 of your water. So go ahead and get this slide, and then I have a picture that I'm going to put it on with the picture and show you how it works with that. And I'll highlight all the same stuff that I did here. And I'm sorry, they put this board down low, and that makes it even harder for you to get your pictures, because now the board's higher than low. So I really like this graph. So let me make it a little bigger, because it has exactly what we just did. Intracellular, extracellular. Who can remind me what percentage of our fluid is inside? Very good, 2/3. What percentage is outside? 1/3. So ignore, look, there's a lot of numbers up there, right? A lot of percentages. Ignore them if we haven't talked about them yet. You don't need that. Okay. Who can tell me how much plasma you have? Yep, about 3 liters of plasma. So how much interstitial fluid? About 12 liters, because our relationship here was 4 times, right? This one's 4 times 1. So I can go like that. It's really that simple. What does ICF stand for? What's that I? In. There you go. Intra. And what does the E here stand for? Very good. Extra. Okay. And that's got it. That's everything. Look how quick it is. Once we've already talked about it, that's it. That's what you need. 2/3, 1/3, 3 liters, 12 liters. Okay. That is our basic understanding of where our fluid is. The biggest thing that makes it a little difficult is at first, the prefixes, people don't remember the prefixes. And then it's been a while since you did interstitial fluid, so some people kind of at first are like, wait, what's your interstitial fluid? Oh, that's just the fluid outside of body cells, out in the tissues. Okay. This next graph is actually one of my favorite things that we do. And at first, let's be honest with you, it looks crazy. I am going to make it not crazy. It is not as tough as it looks. I made it small because I don't need you to see the numbers. This one is not about memorizing any number. What this graph is about is, I know you're going to do the same. You're going to help me out. What's that? Okay, that's a cell. I need to make it a little bigger. So let's go right there. There's our cell. This time we want to focus on ions. You may know we can also call them electrolytes. By the way, they have found out that your electrolytes are so important to hydration, right? How many people ever gone and got an IV for hydration? We're going to try to fight a hangover? Don't tell me. All right. So they realize now that hydration, electrolytes are such an important component of that, not just your body water. If all we do, and it's cool to drink water, but if you're just replacing water without your electrolytes, it's not benefiting your body as much as if you replace it with electrolytes. So for the past couple of years, I've been drinking mineral water, and I stay so much more hydrated, and I don't have to drink a gallon of water a day to stay hydrated. If I drink a half a gallon, I'm great to go. If I drink more, that's cool. But you can stay hydrated with less water as long as you have electrolytes. So those little packets you can put in your water or what have you, that stuff's good for you. Just make sure it's got a blend of stuff. It's going to have a lot of sodium. And what I want to help you understand is we don't need to be afraid of sodium because it is supposed to be the #1 ion in the body. You're supposed to have sodium. If you have healthy kidneys, your kidneys determine how much stays or how much leaves. Okay? So this is crazy. What this is going to be about is what we just did. Where are your electrolytes? Are they inside or are they outside? Now here's the reality. They're in both places. So how are we going to learn it? We're going to learn it very simple. Where is sodium the highest? Where is potassium the highest? Where is this the high? That's how we're going to learn it. So check this out. If sodium, and I heard this, so I'm just going to put it, if sodium is higher out here, that means if there's more sodium outside the cell than inside, then I don't have to write low sodium in here. It's slower in here, okay? So the way we're going to do this, and we're going to go learn sodium and potassium and calcium and bicarbonate and chloride and protein, okay? Probably at some point I'll add magnesium because all of those electrolytes that you drink, they're usually sodium and half as much potassium, and then about a third as much magnesium as the potassium. That's commonly the ratio that they're in. So magnesium for hydration is probably your third most important electrolyte, but we haven't talked about it in A&P too much, so I'm not going to add it today, okay? These that I underscored, they're ones that have been discussed at some point through A&P 2. So that's why I'm making them more important today. Right, don't know if you picked this up in A&P 1 or not when you did depolarization or repolarization. There's an ion that loves to be the opposite of sodium. Sodium's in one place, and this other one, it's opposite, is in the other. And it is potassium. So what that means is you naturally have a higher level of potassium in the cell. The reason that all these electrolytes that you take that are hydrating you give you both sodium and potassium, the potassium needs to go in the cell to hydrate the inside of the cell. The sodium stays outside. Okay. Hey, what's salt? What's the most common formula for salt? NaCl. Very good. NaCl. Sodium chloride. So if the sodium's out here, the chloride's going to be nearby. So look, high level of the chloride ions. They happen to be negative outside. Oh, by the way, electrolytes, there's very commonly a third name. You ever heard take your vitamins and your minerals? The minerals are most of the electrolytes. Not all of them, but most of the ones we're talking about now could be called minerals. Sodium, potassium, magnesium, chloride, calcium. Those are minerals. Have another little memory device here for you. And it's just me trying to do what I can to make this stick easier. There's only 2 ions that you need to know that are higher inside the cell. Only 2. And they both begin with a P. I'm sorry that they use K for potassium, okay? But the word begins with a P. Potassium is higher inside the cell, and so is protein. And I think that's going to be easy to remember when I say this to you. Protein's higher in the cell because that's where it's made. Your proteins, your body proteins, are all made in the cell because that's where your DNA is. Your DNA is in the cell, and the DNA is the blueprint to make protein, and it sends it out on messenger RNA. You may remember this, and it finds a ribosome, and it links up, and that's where your proteins are built in the cytoplasm. So in our cell, we have 2 things higher. By the way, on this graph, yellow means inside the cell. Remember, there may be others, but I'm not doing all the others, okay? If I did do this, though, oh, cool, it also starts with a P. Next one, calcium. There's very little free calcium in the cell. Most of the calcium in your cell, in your muscle cell, would actually be contained in the reticulum, so it's not really free throughout there, which is pretty cool. But calcium is higher outside. This one, which we'll talk about a little later today, which was covered back in cardio when you did your lectures, that is the bicarbonate ion. That is the #1 chemical buffer in the body. We'll get to buffers right at the end of today. And so bicarb, you may remember this from digestive. Bicarbonate is what the pancreas makes to neutralize the acid that comes from the stomach. And so the pancreas makes it, and it dumps it into body fluids, and it gets into your blood. So it's outside the cells in higher levels. And so that's our list. The way that there's going to be one other main thing I say over here. The way that this goes, red is plasma. They made blue interstitial fluid, and the yellow is inside the cell. So if you are interested, and maybe when you work in healthcare, if you work with one of these ions a lot, you'll become familiar with the numbers. And maybe in some of the classes, they'll have you learn some of the numbers. I teach it like this, relationship-based, so that when you get in your program, hopefully your mind can go, oh yeah, when we did electrolytes, we learned where they were highest. So you know whether it's highest outside the cell or inside the cell. And then you can start relating the numbers to it. Look how crazy this is, potassium right here. Look how high it is in the cell, but there's its level outside the cell. I mean, huge difference. Here's sodium. Outside of the cell, wow, massive, versus inside the cell. Almost all of these ions, the two extracellular compartments, remember, outside is interstitial fluid and plasma. On almost all of these, when you see red and blue, they're almost at exactly the same height, or they're super close. There's only one item up here where there's something in a significantly different level between the blood and the interstitial fluid, between the plasma and interstitial fluid. And that's right. Look, protein's highest in the cell, right? It's almost non-existent. You can't even see where my finger is, where the little pointer is right there. You can't even really see blue because there's almost no protein in your interstitial fluid because it moves into the lymphatics if it was there. It's not going to stay outside the cell. But there's one big difference, and that's this right here. You may remember this from earlier, and this is kind of why I teach it. Plasma is 8% protein. So there are definitely proteins in the plasma, although there is almost no protein in the interstitial fluid. So there's your ions. You may be asked on the test, which ions are higher inside, which ions are higher outside. There may be some kind of multiple where you have to pick them or something like that. That's what this is all about. So most of what I like to teach you from this is the pictures, the graphs and stuff, because it has a better chance to stick. There's some stuff that I'll do that doesn't have a graph. And some things I'll remind you about, we'll just go to a blank screen and do it. This is excellent because it's all about helping you understand your water on a daily basis, how much goes in and how much goes out. And the concept is very simple. It should be the same. The amount of water that we get on a daily basis should be the amount of water that leaves. What if it wasn't equal? We'd either swell up or we'd shrink down. If every day you lost a lot of water, you'd shrivel up, eventually die. If every day you gain a little water, you'd swell and swell and swell and swell and swell. Okay? What you already know about this is how you get most of your water. You know that most of the water comes in from drinking. And so I do want you to know the percentages over here, okay? About 60% of the water comes from drinking. About 30% of the average person's water comes from food. So if you love cucumbers and you eat a ton of cucumbers, then you probably get more than 30% of your water from your food because they're very well hydrated. If you cook everything you eat and you love to cook it till it's cooked to death, then you probably get more of your water from liquids than you do from your food. So this varies. Just Just understand that. But these are the numbers that may show up on the test. That's what that means, is in the electron transport system, that water that we made when we convert the NADHs and FADH2s, that water that we made equals about 10% of your daily water. Okay? I'm not going to ask you the milliliters. All right? I just want you to know the percentages, the relative percent. And the cool thing about this is water that goes in. Cool thing about the water that goes out, the amount that you drink in is virtually the same as the amount that you urinate out on a daily basis. That's pretty cool. It's going to be approximately 60%. This right here is so close to 30%. I'm not going to try to be all exact and have answers and say, ooh, is this 26, 27, 28, or 29%? It's not about that. It's about the true understanding. And that is this. That we ate in approximately 30%, a little less than a third. And that's very close to the amount of water that escapes through your mouth and your nose and your skin on a daily basis. You don't know it right now, probably, wherever you are, but water's coming right out your skin. You don't feel it. We're not talking sweat. We're just talking evaporation. It comes out of your skin and you don't even know it. Oh, man. I didn't wear my glasses today. First day all term. I was going to do this and fog up my glasses, and I'm not wearing them. So if you're wearing glasses and you want to do this, you don't have to. If you just go like this and breathe out, you'll trap the water. It'll fog them up because every breath, we're letting so much water out from our lungs. We don't even know it until we trap it, right? Or if it's super cold, you see it coming down. But other than that, we don't. Okay. So loss through the skin and lungs is about a third. And then look at this. Sweat, about 8%. And in your feces, about 4%. What would happen to that 4% if you have diarrhea? It'd go way up. What would happen to that 8% if you're going to be working outside in the West Texas summer? Oh, it's going to go way up. So use some logic on this, but these are normal numbers. These are normal, regular numbers. Notice, and this is about the relationship thing here, typical person will sweat out twice as much as is in their digestive waste. And then just for fun, I like to add this when we talk. What if every day for this year, that 1 ounce, let's say you're doing that thing where you drink a gallon of water a day. I don't know if you know, a gallon's 128 ounces. What if just one of those ounces, that's less than 1%, one of those ounces stayed in you? But tomorrow, another ounce was added to that. And the next day, every day, your body just couldn't get rid of 1 ounce. So just 1 ounce stayed. That means in 1 year, you have 365 ounces, right? Because that's how many days. You'd have 365 ounces. Anybody know how much water that is? It's about 3 gallons, and water weighs about 8 pounds a gallon. So if you retain 1 ounce a day of water, that would be like 24 pounds of water in a year. That's crazy. So that's why this is so important. What goes in should come out on a daily basis overall. Cool. All right, now I'm going to remind you of something we did earlier in the year. Ooh, what's that stand for? Yeah, atrial. Atrial natriuretic. And you remember they could call it peptide, right? So they could do ANH or ANP. What did that part mean? Sodium. And tell me, where did that sodium go? Nice. Into the urine. So this is your reminder. because this chapter is all about water balance, and this is a hormone related to water balance. So we're going to talk about the water balance hormones again. ANH causes sodium to go into the urine, right? The kidney was your target because the kidney is what makes urine. Who could tell me what tissue type that is? Yeah, that's simple cuboidal. This is supposed to be a kidney tubule. And there's a capillary right there. So if in we know, peritubular capillaries from last time. Let's call this a proximal convoluted tubule. Doesn't have to be. But if sodium moves into the urine, that means this, that the sodium that was there goes here. So we get higher sodium here. What follows sodium? Water. So there you go. Oh boy. I think we found a weak spot of the board. So that word is supposed to be urine. Okay. So we make more urine. But what we've really done is we've lowered our blood volume and we've lowered our blood pressure. So there's a reminder to you about ANH, how ANH works and what ANH does. And wow, the board definitely does not give me as much room as it used to, because do you remember what I'm going to put on the other side? What's the opposite of ANH? Ooh, what's the antagonist of ANH? There you go. Aldosterone is the antagonist. So it causes, look, I'm going to say it in a different way. I'm going to be fancy. Reabsorption. Which way does reabsorption mean? So that means it increases blood volume and blood pressure. And ADH created little pores called aquaporins. You might have heard that in the lecture, but I didn't do that with us in the lab. But what ADH does is in the tubules of the kidney, specifically the collecting duct, it makes these little channels where water can move. So ADH causes reabsorption of just water. It doesn't have to use sodium. So it also increases blood pressure and increases blood volume. And so there are your antagonists with relationship to blood pressure. So make sure that you study those again, okay? And snag that picture again. ANH and aldosterone are true antagonists because they both move sodium in opposite directions. Remember, our memory device was natriuretic, sodium in the urine. So the opposite of sodium in the urine is sodium into the blood. Okay? And ADH does the same thing as aldosterone, just does it different. Doesn't need to move salt, only moves water. How? By building little channels that lets the water move. So that's how it does it. So now I'm going to go a long way. I'm just going to skip a bunch of stuff. So you may have heard this before. In lab, we didn't talk about it much. It's been in some lectures, but I just want to make sure everybody understands what edema is. Edema is excessive tissue fluid. Tissue fluid is interstitial fluid. So it's when you get swelling in the tissues, an increase in interstitial fluid, or as we were seeing at Caldwell ago, ISF. Okay, that's all I'm going to do here. Just snag that to make sure you understand what edema is right now. I want to remind you about parathyroid hormone. What is the antagonist of parathyroid? Calcitonin. So what do you remember about calcitonin? So it lowers blood calcium, right? If calcitonin lowers blood calcium, what does PTH do? if you lower blood calcium, you're taking it out of the blood, do you remember where you're going to put it? You put it into the bone. Which cells build bone? So calcitonin takes calcium out of the blood and stores it into your bones. Parathyroid does the opposite. And in fact, it has 3 targets: bone, kidney, and the intestines. Which bone cells would PTH activate? Osteoclasts. Why? Because they're the opposite, right? Because they're the opposite, because we want to do the same thing. The opposite thing, sorry. So there's a little reminder about the differences between parathyroid and calcitonin. PTH and calcitonin. Okay, our next topic. This is pretty big. Acid-base balance. So I'm going to make that little because I'm going to write all around this. I don't know if you remember pH scale from A&P1, but there's the pH scale goes from 0 to 14. What's right in the middle here? Very good. Oh. 7 is right there. And 7 is considered very good. Neutral. Do you know about what do we call anything lower than 7? Yep, an acid or acidic. And what do we call it if it's higher than 7? Basic or a base? What's the fancy word for base? Yes, it's alkaline. So it's alkaline. So we have acids and bases. Bases can also be called alkaline. Now, what they want us to do, realistically, is to think about blood. The pH of blood. And right now we're doing arterial blood, okay? Nice bright red blood. pH of your blood is about 7.35 to 7.45. Why did I put it on that side? Because it's a little bit basic, okay? It's a little bit basic. When we write pH, it's a little p and it's a big H. pH basically tells you the concentration or the percentage, so to speak, of hydrogen. How much free hydrogen ions are in a solution. So that's what you want to lock in. The key factor with pH is it's all about hydrogen ions. If hydrogen ions are somewhere, it's acidic. If you take them away, it might become basic, depending upon how many there are. Okay, that's the big concept. And so look, blood, if we average those two and say blood is 7.4, well, it's very slightly what? Basic. But here's what I want to help you to understand. What if we went, so what if the pH goes to 6.4? Okay, so it went to 6.4. Do you know what that means? It means you'd be dead. That's what it means. That one number, that change in 1 from 7.4 to 6.4 would actually kill you. What? Yeah, it would kill you. You can't live at 6.4. Do you know why? Because pH is not, these numbers are not just single numbers. Every time you move one number, one full number on the pH scale, it's a power of 10 change. That means 10 times this way, more hydrogen. So what does that way mean? Let's say it this way. That's hydrogen. If you get more hydrogens going that way, what do you get when you go that way? Less, fewer. Fewer hydrogens make it basic, more hydrogens make it acidic. Every time you move one number, if you go to the acid side, you're getting 10 times more hydrogens. What if we went from 6.4 to 5.4. How much more? Well, just from there to there is 10 times, right? But you know where I'm going, where I want people to know. If you're supposed to be there, and then you go to here, 7.4 to 6.4, 10 times. 6.4 to 5.4, 10 times. That's 10 times 10. What's that? 100. What would be 100 times 10? Oh, that'd be 1,000. Every time, I'm going to put this here. Did you know that your stomach acid can get down to 1.4? It's about as strong as it can ever get. Some people's may not get that far. It might just get to 2. Here's what I want you to see. Your stomach is made to be acidic. It has cells that line it, right? And it has mucus that lines it on the inside. I don't know if you know, the average stomach cell doesn't even live a whole day. The lining doesn't even live a day. Your stomach lining replaces itself every day, multiple times a day, because it's a harsh acidic environment. It's rough on the cells. They keep getting recreated. Wow. How much more acidic is the stomach than your blood? Are you ready? We'll do it together. Let's do it together. 10 times, 100 times, 1,000, 10,000, 100,000, 1,000,000. Your stomach acid has the potential to be 1,000,000 times more acidic than your blood. That is not bad. It's supposed to be like that. Maybe from digestive, you might remember that acid in the stomach activates the enzymes. It allows digestion to happen. If your stomach were up here at 5.4, you wouldn't activate the enzymes and you wouldn't break down your proteins. And you wouldn't kill bacteria.
How acidic is the liquid?
How's it about there? About 2, 1.4 to 2. Yeah. Depends on the lemon, because some lemons are sweeter than others.
How can your pH drop to like 6.4? Like what could be associated?
Oh, we'll get to that in a little bit. So your pH won't go that low, but we'll talk about pH changes later. Okay. Because that's where we're going with this, but we have to get this and start doing little steps to get there. Over here, you knew where I was going. Your duodenum is about 9. It's made to be there, okay? With all those dots, maybe you can't tell, that's supposed to be 9.0, okay? That's normal. Remember why we have our digestive sphincters to compartmentalize. And by compartmentalizing, the stomach can have a pH that's lower. It's not going to sit at 1.4 forever. You fill it up with stuff, it dilutes it, it changes the pH a little. But the stomach's going to go between commonly 4 and 2 is where it kind of fluxes, maybe down that low. If you're taking antacids all the time, if you have heartburn and reflux and you take antacids, you drive the pH up in the stomach. It doesn't kill the bacteria, and then you won't digest your protein. And then your protein gets pushed into your duodenum, where it's not supposed to have to do all the work, which then has to do all the work. So it may not spend enough time in there to be fully broken down. So you may not absorb as many proteins as you need. Go ahead and, no, not yet. Let me tell you something else. What if your pH is too low? Let's say 7.3. Or what if it's too high, like 7.5? What in the world is that all about? Well, when something is out of whack, we usually give it a name, right? Like if you have a disease, they give it a name. You have to describe it. So if your pH changes, they give it a name. If your pH is outside of the range, If it's too low, it's too acidic. If it's too high, it's too basic. So watch this. This directly relates to test questions, okay? They call a pH in the blood that's too low acidosis. They call a pH that's too high alkalosis. Okay? If it's too low, it's called acidosis. If it's too high, it's called alkalosis. What is a pH of 7.35 called? Normal. What's a pH of 7.45 called? Normal. What's 7.39? Normal. What's 7.41? You get the idea? Okay. So I'm going to have a test question that's going to have all these numbers. It's going to ask you about one of those numbers. And you tell me, is that normal? Is it acidosis? Or is it alkalosis? Where is our normal range? 3.5 to 4.5. In that range, and that includes the 3.5 and the 4.5, those are normal. Has to go outside of that to be acidosis or alkalosis. Has to go outside of that. So you got it. That's the picture. So the next thing we're going to do is we're going to talk about buffer systems in the body. And the first type of buffer we're going to discuss are buffers that use chemicals, chemical buffers. There are three major chemical buffers, but what I do with this last chapter is I try to reinforce, you may have noticed, trying to reinforce things you've already done in A&P, whether it was A&P 1 with acid bases or something we've already done in A&P 2 like ANH and aldosterone. So if you see these three words, the one that we have done the least with is phosphate. When we talked about phosphates, we talked about phosphates with ATP and energy. And so I'm just going to leave it at that. What I want to highlight right now is these two. Bicarbonate and protein. Bicarbonate and protein. These two molecules are great buffers. Bicarbonate and protein are great buffers. And what a buffer does, look right here, it resists a pH change. It either resists a pH change or actually works to change the pH if we need to. And so, here's how. So what I'm going to show you is what these two chemicals are and how they work. First off, bicarbonate. HbO3 negative is its formula. All right. What little ion makes something an acid? Hydrogen. If we have a lot of free hydrogen, then something is an acid. So here's the cool thing about bicarbonate. You can take that hydrogen and add it to this. And look what it would become. Right? It just had one H. Now it's got two. Well, when you take these, when they're free, something's an acid. When you bind them up, they're no longer there. Now it's not acidic. So the way that this molecule buffers is it can absorb hydrogen. And so if something's an acid, it can absorb the hydrogen and it can change it. Okay? Or, if need be, that molecule can let go of a hydrogen to make it an acid. So what I want you to understand with these chemicals that are buffers, they can either pick up the acid or let it go. They can pick it up or let it go. And that's how they change and or resist a change in pH is by what they do with that. So how in the world can a protein do that? Well, here's how. Okay, I know it's been a while since you had AMP1. What I have just drawn for you there. We've done so many AAs in AMP2. Who knows what that one is? What is that thing? NH2, CH2, COOH. There you go. That's an amino acid. So that little AA right there, that's the formula for amino acid. And this ain't gonna be on no lab test. You're not gonna have to draw that out. Okay? But here's a good reminder. An amino acid is a molecule that has a certain number of atoms in it. And it has a carbon chain, and it's got some hydrogens and nitrogen and oxygen. That little R group, don't worry about it. That's what makes each one a little bit different. Here's what they can do. They could just give up those hydrogens. What if an amino acid gave up a hydrogen? What does it make the solution out there? Acidic. What if the amino acid took on the hydrogens? They would take the acid out of the solution and they could make it more basic. So a protein and bicarbonate can work the same way. They can go out there and they can either absorb or release their hydrogens. And that's how they buffer. Proteins, not as much, but still very important. Go ahead and snag that picture. This isn't so much about the formulas, but the honesty is by seeing the formula, you can see where the hydrogen comes into play, and that is important to understand. So we have chemicals that buffer. We also have systems that buffer. Your entire physiology of a system. So the two main systems, I'm going to use a pen as little as possible now. The two major systems that regulate your pH, remember what a buffer does. It's regulating your pH of your body. Would be respiratory system, and that's all about breathing. So I'm going to try to write the word breathing over here. And what does renal make? There we go. Renal makes urine. So what if you pee out hydrogen? What are you making the body? More basic. Isn't that cool? If you pee out hydrogen, you're making the body more basic. Okay? When you breathe and you breathe out, do you remember what you breathe out? You breathe out CO2. So you're actually lowering your CO2 when you breathe. What if you held your breath? You would raise your CO2, right? So what I'm going to show you is there's a relationship between CO2 and hydrogen. And that relationship, they always move the same way. So the more CO2 you have, the more hydrogen ions in your blood. What does that make the pH? More hydrogen makes the pH acidic, which is, let me just remind you, right, a low pH. So what we do is we regulate our breathing, and our kidneys regulate our production of urine to manipulate our pH. Okay? I only have a couple more things I need to do with you anyway. We've almost made it to the end. This formula right in the middle, take a picture of that formula. Here's why. Just a little. If we raise this, we automatically raise that. If we have more CO2, we get more hydrogen ions. And more hydrogen ions make something what? Acidic. Makes something acidic. Makes the body acidic. If you get rid of your CO2, you lower your CO2, then you naturally lower your hydrogen ions and you make it more basic. What does that word mean? Hypo? Hypo means lower, and ventilation means I want more confidence though. Hypo means it won't let me. Hypo means lower, and ventilation means breathing. Okay? Hypo means lower, and ventilation means breathing. So watch this. I'll try to find our way back somehow. I don't know if I can. Let's see. There it is. How could breathing less cause a condition known as acidosis due to the respiratory system, or respiratory acidosis? Breathe less. What do you breathe out? CO2. So you breathe less, you hold your CO2. You build up your CO2. What moves with CO2? More CO2, more hydrogen ions. So now you're building up your hydrogen in your blood. When you build up your hydrogen, that makes something an acid. So you're making your blood an acid because you're not breathing enough. You're holding your breath or you're breathing shallow. Okay? So if you have a broken rib, do you think you're going to want to breathe a lot? Tell me why. Ow! It's going to hurt. So you're going to breathe less. So you're in danger of respiratory acidosis from anything that causes hypoventilation. Some things, like a broken rib, it might be pain, but sometimes you can have damage to the brainstem. The brainstem mediates your breathing. The opposite is also true. Too much makes it go the other way. Snag that picture and let's just see if I can make it. At least that'll put a little highlight there so you'll know which things I want you to focus on. For renal is what organs? Kidneys. And what's the waste product your kidneys make? Urine. Can anybody tell what that is? Hidden in the dots? Bicarbonate. That is HCO3 negative. What if we put it into the tubule? What word did we learn it's called when we put something into the tubule? See me just trying to be good, hoping it works. So if you put bicarbonate into the tubule, you're going to get rid of it. Getting rid of, wow. Look at this. If you lose a bicarbonate, it's the same thing as gaining hydrogen ion. So if you do this, you make your body acidic. I'm only showing you one direction, but the opposite is the opposite. So this is showing you. You can get rid of hydrogen ions, you can pee out hydrogen, or you can hold on to hydrogen, but you can also pee out bicarbonate or hold on to bicarbonate and have an effect. Whether you move bicarb or hydrogen, that would make the effect the opposite. So if you get a question about this, you just want to go slow and you want to think about that last little phrase. If you get rid of bicarb, it's the same thing as holding on to it. Okay? And that will help you work your way to the answer. Go ahead and snag that picture, since I can't trust that I could put much more up there. Oh yeah, we don't need to go through all that technical crazy stuff right here. So what does respiratory relate to? What system? Oh, the respiratory system. What process? Breathing. So if when you're working or in a program or taking a test and you see respiratory acidosis or respiratory alkalosis, it means you're too acidic or too basic because of breathing, because of a problem with your lungs or your breathing mechanism. If you have acidosis in the body, your pH is too low, for any other reason, it's called metabolic. Okay? So they basically say there's two types of acidosis, respiratory and metabolic. If it's a breathing problem, it's respiratory. If it's any other system problem, which may be urinary, but it might not, it might be something else, we're going to call it metabolic. Okay? So they're separating acidosis and alkalosis into two categories based on breathing and pretty much everything else. Okay? That's what this means. You may want the picture. There could be a test question show up about those two. Acidosis means the pH of the blood has gone which way? Acidic, which is, yeah, lower. There was our box, right? I thought we had it made. There you go. Okay, so now you can get that picture. That's close enough to what I wanted to do. So the breathing part is pretty self-explanatory, so we're going to kind of skip to the metabolic part to help you understand a few other things. Alcohol is an acid, okay? Alcohol is an acid. So if you drink too much alcohol, you would become what? Acidic. And that's not a breathing problem, so they would classify it as metabolic. Okay. Anything that causes you to lose bicarbonate. This is a very important thought. Pancreas puts bicarbonate into your duodenum. If you have diarrhea, it pushes it out way too fast. It doesn't have time to buffer that acid. Okay, so you would by losing the bicarb and losing that buffer, you would become acidic based upon that. So those are the kind of the two big ones that I wanted to focus on. It gives you a whole list of things, but those are the two biggies. So if you want to snag that picture. Oh, sorry, I didn't. Okay, now you can get it. So what process do you, no, never mind, because I know what you're going to say, and it's not going to be it. It's okay. So we'll get rid of that one. So if it moves out too fast, we call it diarrhea. But what if your stomach contents come flying out your mouth? What do you call that? Oh, vomiting or throwing up or emesis. Give patients emetics. Oh. If you're throwing up, what was in your stomach? Acid. So you're getting rid of the acid. So if you throw up and you get rid of the acid, then your body, if you throw up too much on a regular basis, then your body can become basic. Okay. Also, very common. So let's say you have heartburn. take a bunch of antacids. And then your stomach starts feeling bad and you throw up. One, you took a bunch of antacids and they get soaked into your blood system. So they're already making you a little basic. And then you throw up on top of that. And now what happens, this is the long-term thought of that. Your blood in your stomach has to put the acid back in there because that's what the stomach needs. It needs the acid in the stomach. So it takes more of the acid out of your blood. So your blood just got more basic. So throwing up, one of the reasons it's bad is because your blood has to replace the acid into the stomach. So it makes you basic. If you take antacids on top of that, it makes it more basic. So it can compound. People with digestive problems don't necessarily understand that, and it can be a big issue for them. So go ahead and 2 more slides, 2 more minutes, probably all it's going to take. Here's your first slide. If your pH is below 7, what do we call it? Yeah, it's acidic, so it's acidosis. This is acidosis. That slows your nervous system. Everybody depresses your nervous system. That can cause you to go into a coma, and it can actually kill you. Okay? So acid depresses the nervous system, can lead to coma and death. If it's basic, it excites the nervous system. That can lead to convulsions, excessive contractions, and your diaphragm is a skeletal muscle. Can seize up the diaphragm. That's respiratory arrest where you couldn't breathe. So important to note, both acidosis and alkalosis could potentially kill a patient, okay? Both ways, not just one. As they said in the previous slide, acidosis is more common, but alkalosis can happen